All right, looks like we got a solid turnout here, so let's begin. I want to welcome everyone to this webinar and thank you for joining. Today's webinar topic is for Simcenter 3D, saving time with Assembly FEMs, where we'll learn more about Assembly FEM creation, different connection types, node and element numbering organization, and much more. My name is George Farah. I'm a business development engineer here at ATA Engineering. I'm based out of our Denver office, and I'm happy to be joined by our very own Daniel Kaminsky for this topic. Daniel is a very experienced Simcenter 3D user and is also a Siemens certified expert. Before we dive into the actual content, here's some housekeeping notes. All attendees will be muted throughout the webinar. If you have any questions, please type them into the chat and we'll have the presenter answer them at the end of the presentation. This webinar will be recorded and will be available on our website and our YouTube channel. Before I hand this over to Daniel, I want to give a quick overview of ATA Engineering, who we are, and how we might be able to support your team. ATA is a high-value engineering services company helping our customers tackle the toughest problems. Engineering services make up about 70% of our business, with most of that work focused on the aerospace and defense. As you can see here, we have our hand in many different industries, including themed entertainment. So who are we? Well, we're a highly skilled employee-owned company with a full-time staff of around 220 people, most of them having an advanced engineering degree, as you can see on the right. We have 9 national offices across the United States, and as I've mentioned before, we have years of experience focusing on design, analysis, and test, providing high-value engineering services and great quality. This includes everything from structural design, structural dynamics, thermal, vibroacoustics, fluid dynamics, and more. Test-wise, we are the leading independent modal test group in the United States. We have a lot of experience flying our team out to the test article location and to conduct ground vibration testing and using that information to help drive model design. We've talked about the engineering services side of the business, and now that leads us into our software side. We're a Siemens VAR, a value-added reseller, who not only sells the product, but also provides software support and training to our customers. We really focus on the products and solutions that we use in-house, primarily on design, analysis, and test. For example, we use NX for design, FEMAP, Simcenter 3D, Star CCM for simulation. For test, we are the first and now the only, or one of the only Siemens partners in the United States that can provide Simcenter testing hardware and software. One thing that sets ATA apart is that we sell what we use, and because of that, we've seen past customers truly appreciate our expertise with these tools. This has been proven over and over again through our hotline support, where you're actually speaking with a well-versed and experienced ATA engineer. In addition, we teach a variety of classes primarily dealing with simulation, and we actually generate all the Siemens training materials for NASTRAN as well. I want to encourage everyone to visit our ATA website. You can find all kinds of information on here, including our technical support hotline for customers who have purchased software from us, as well as free resources, including past webinars, FEMAP APIs, and white papers, all of which are available to download. With that being said, I'm happy to introduce today's speaker, Daniel Kaminsky. So Daniel Kaminsky is a project engineer with over 10 years of experience using Siemens Simcenter 3D for structural and dynamic analysis. He holds an expert level certification from Siemens, demonstrating advanced proficiency in applying the software to solve complex engineering problems. His work focuses on building accurate finite element models to predict failure modes and support critical design decisions. Daniel holds a Bachelor of Science in Mechanical Engineering from the University of California, San Diego. Take it away, Daniel.
All right. Hello, everyone. As mentioned, my name is Daniel Kaminsky, and I will be walking you through today's webinar on using Assembly FEMs in Simcenter 3D. Simcenter 3D is a software that I really believe in, and as George mentioned, I have used it a ton in my aerospace-related analysis projects. And in our webinar today, we're going to talk about creating assembly FEMs, which are a really useful feature of Simcenter 3D. And essentially what we're going to do is we're going to go through the entire assembly FEM creation process. So that's going to go from idealizations, meshing, model connections, and post-processing. And in doing so, I'm also going to give some relevant Simcenter tips and tricks. So I'm hoping even if you are familiar with the assembly FEM process, that you're going to learn some new tips or tricks today that's going to increase your efficiency. So we're also going to talk about using the assembly label manager. So that's going to talk about a really useful feature of assembly FEMs, how we can deal with node and element ID. Node and element ID overlaps in our component FEMs. We'll also talk about modifying your geometry and how those modifications can propagate throughout your assembly FEM. We'll talk about replacing your component FEMs with updated FEMs or super element representation. And then we'll get into creating some connections within the assembly FEM. So mainly going to talk about using the bolted connection tool as well as glued connections. And then finally, we'll talk a little bit about post-processing. All right, so why use assembly FEMs? There's some really critical reasons too that are listed on this slide. First is improved workflow for large assemblies. So what's nice about assembly FEMs is they're going to mirror your CAD assembly structure, and that's just going to really help you simplify management of those really large and complex assemblies. Being able to reuse component models. So this is one of the ones we're really going to focus on today, and really where AFEMs shine is being able to, say you have repeating components within your assembly. All you need to do is mesh just one iteration of that component, and then the assembly FEM will map that individual FEM iteration to all of the locations throughout the assembly. So really useful feature there. Efficient updates, as always. Simcenter is so great about letting you leverage that geometry associativity such that when you need to make quick design changes or modify your geometry, you can easily do that and have that change be reflected not only in your individual FEM, but also propagate throughout your entire assembly FEM. Collaborative environment and distributed workload. This is two other aspects that are also really important and really useful for assembly FEMs. Usually, if you were to just set up a single FEM that you're working on for an entire assembly, you essentially can just have one user have that finite element model open at one time. But by leveraging assembly FEMs, you're able to break up that assembly into sub-assemblies or sub-components, and then have people working on those individual FEMs in tandem. And that just means you're going to be able to increase your efficiency, and that also means you're potentially going to be able to manage the organization of the model as well by having people maybe work in their individual folders for those individual sub-assemblies or FEMs. Centralized data management. You can take advantage of platforms like Teamcenter to store your assembly FEMs, and that's just really going to be great for that data traceability and control. And dealing with those node and element ID conflicts, like I talked about with using the assembly label manager. All right. So with that, we can actually go ahead and jump into our live demonstration portion. So I am showing right now a assembly here within Simcenter 3D. And again, this is a perfect candidate for using an assembly FEM because we have repeating components. So we have, in this case, just two components. We have our tubes, which there are 12 instances of, and then we have these corner brackets, which there are 8. So we can go ahead and create our assembly FEM. And then what we're going to be able to do is start creating those individual component FEMs. So for example, we're going to start with those tube components. And you have a few options here. The main ones being you can map an existing FEM that you've already created, or in this case, we're going to create a new FEM. So now we have our FEM created for our tube components here, and you can see we have all of those instances of those tube components. If you want to change how those are represented within our assembly FEM structure here, you can do things like pack, and you can see it just is telling you now you have essentially 12 iterations of that tube FEM. And then what we can go is actually start creating the mesh for this individual component FEM. So what we're going to do for this tube is a mid-surface 2D mesh. So before we do that, though, I want to talk a little bit about leveraging some of the really powerful synchronous modeling tools within Simcenter 3D. So one of the most useful is the delete command, and this is really useful for being able to defeature things. So for example, maybe we want to remove all of these filler radii. And what's really great is these synchronous modeling tools also have this face finder capability. So for example, I just have one fillet radii that I've selected, and then I can leverage the face finder, and it's going to automatically select all of those equivalent fillet radii. So that's just going to save you clicks. And that's something that I've always really appreciated about SimCenter as well, is how it can save you a lot of clicks by leveraging some of the really powerful selection tools within the software. And if you've done a lot of preprocessor and mesh setup, you know, saving clicks can equate to a ton of time in the long run. So with that, we've done our defeaturing, then we can go ahead and create our mid-surface. The mid-surface command by itself could probably be a webinar in and of itself. Really powerful command. The main thing I just wanted to point out for today's demonstration is this stitched edges toggle. So this is something that's really great to have turned on as well. So what this will do is tell our FEM file that hey, all these sheet bodies that have been created by this mid-surface command, I want you to have stitched edges across those sheet bodies. So essentially merged the nodes across those sheet bodies. So once again, this is just saving you from having to do an additional command within your FEM file, which is also really nice. So what's also really great about SimCenter is being able to take advantage of good visualization feedback. So for example, we just did that stitch edges toggle. What we can do is within our FEM file, we can go to our polygon edges options, and we can turn on both our free and stitched edges. And then we can visually confirm with our geometry that it seems to be that our stitch edge operation was in fact defined correctly, and we're getting stitch edges across our sheet bodies where we expect. So that's something, again, that I appreciate about SimCenter as well, is having these types of visualization feedback like this to be able to confirm that the software is in fact doing what you expect. So now we can go ahead and create a mesh on this component. So for this example, we're just going to do a simple 2D mesh here, 2D mapped mesh. So you can see that we got a good looking mesh now. And next, what you would usually do is define your shell thicknesses. So one of the other tips I wanted to point out is leveraging the edit mesh associated data here within SimCenter. So we can tell it, hey, for my thickness, instead of coming from the physical property table, I want it to come from my mid-surface operation within the idealized part. So this is really great. You can potentially manage or imagine if you have kind of complicated tapered thicknesses or things like that. Instead of having to manually create a bunch of properties, physical properties for those different thicknesses, you can just use this option here. And there's a few different options of how it will evaluate those thicknesses. For our example, since we just have our nominal thickness for this tube, it's going to give us the same result no matter what we select. But again, these can be relevant, again, if you have tapered thicknesses, things like that. As always, I recommend, if you're interested in any of the settings you're looking at in your dialog box, leveraging the mesh associated, or excuse me, leveraging the on context help within those dialog boxes to actually open the help for that exact dialog box and see what all those different settings are doing, which is something really useful feature to yeah, really understand all the options within your current dialog box. So again, we're just going to go ahead and use average feature thickness for this example. And then what we can do is leverage things like solver syntax preview to actually confirm and see how this will be written out to Nastran. So, and having set it up like this with importing the thickness from the mid-surface, it's actually going to write it out to our C quad 4 card, as you can see here. And these are the thicknesses that are listed here that it's determined for each node. So yeah, really nice feature there as well with the solver syntax preview to be able to understand how things are going to be sent to Nastran, which is really the most important, right? You want to actually understand how it's going to go to the solver. Next would be defining some material properties. Again, we don't need to define a thickness here on our physical property table because of what we set up with our mesh associated data. Let's see. Sorry about that. Let's try that again. Let's see. Appear to be getting an error with our material properties. Okay, we can come back to that. It may just be, I have a material database, and unfortunately that file may have um, gotten corrupted when my system had to reboot this morning. So what we would do now, though, is we can just jump into our Assembly FEM. And you can see now we have all of our instances of our sheet mesh or of our shell mesh here for those tubes, and they have all been mapped to their relevant locations within the Assembly FEM. So again, we just have one instance of that tube FEM, and it has been mapped to all of the relevant locations. We can also do additional checks within the assembly FEM if we want. Maybe we want to do our element edges check and then confirm again that in fact we have our merged nodes across our sheet bodies. So you can see that here. And yeah, this graphically looks what we would expect for having our merged nodes, which is great. Next, what I want to do is go ahead and actually save this FEM. And I'm going to go ahead and save it in its own specific folder. So we can do that now. And what this is so useful because, again, you can have users using their working in their particular directories. And then you can make sure that you have that organization by not having a folder that's all cluttered and overrun with individual parts. So this is something I always leverage when using my assembly FEMs for my projects. When I have a bunch of engineers working on it, I'll have those engineers working on their individual folders. And then what I can use within the assembly FEM is our assembly load options, and I can specify particular search folders that I want it to load all of the individual components from. So again, you can have all of those users working on those search folders, or excuse me, working in their individual folders. And then you can specify all those search folders that you want the assembly FEM to read and import all of those FEMs or part files, anything like that. So really useful feature, again, with the assembly load options that I definitely recommend taking a look at. There's some options down here for how it's going to load in structure, things like that. These are also potentially relevant settings that, once again, I recommend looking at the on-context help to get some additional details about. But these can be useful for if you have a really large model with a bunch of geometry and your system's getting bogged down a little bit for being able to help alleviate issues like that. All right, so now let's go ahead and create our corner bracket mesh. So we're going to go through essentially that same process. And once again, we're going to go ahead and create a new main part here. And for this component, what we're going to do is just create a 3D TEP mesh. So we're going to use our 3D TEP command here. And again, tons of different settings here for our TEP mesh that you can leverage. Simcenter is really great about having all of those really fine-tuned geometry or mesh setting controls available for you. Some of the relevant ones, you can do things like minimum 2-element through the thickness. That can be useful, particularly if you have a component where you want to capture some accurate bending stress. You can determine how the mesher will deal with small features and how it'll potentially remove some of those like silver surfaces, things like that, which can be very useful as well. But yeah, once again, just SimCenter is so great about giving you all these fine-tuned controls and how your mesh will be created. So let's go ahead and create our tap mesh here. And you can see like that, we get a good looking tap mesh. And we can go ahead and do things like element quality checks and confirm that, in fact, we get no failed elements. And that's something I appreciate as well, just having the ability to do these types of checks, again, within the preprocessor before you have to actually solve the model. That way you can actually clean things up as necessary before getting farther down the line. All right, so now we've essentially finished both of the meshes for our two separate components. So once again, if we return to our assembly FEM, you can see that we have our meshes for those components. So we have all of our instances of our corner brackets, as well as all the instances of our tube FEMs. So now you can do things like play around with your visualization settings. So for example, maybe you want to change the colors of all these individual FEMs. You can do things like base these on physical property tables. So you can see that'll essentially kind of randomize your colors for each instance of your FEM. Maybe you want to do things like change your element edges colors. So you can do things like that also. So I'm going to make these both these shell and tap mesh element edges darker. And again, this is something that's really nice about Simcenter. I always leverage these the ability to make useful FEM pictures like this for my reports or to send to colleagues, just to help people really understand what's going on in the in your finite element model. All those settings we just did, by the way, can be set as defaults within the within your customer defaults. So we can go to our settings in here. So for mesh display, you can set the edge color to actually always be those darker black edge colors if that's something you prefer. And same with that model display option we just set up with that randomized color. You can do that as well right here. So you can do it based on physical property table, material property tables, and so on. So really nice that you can also set these as defaults as well. If those are the types of settings you're redoing every single time, SimCenter gives you the capability to define those defaults. All right, so now let's talk about what happens when you maybe want to modify one of these components. So let's return to our corner bracket here. And let's go ahead and say we want to edit this part. I'm just going to do a simple example here, and I'm going to make it a pretty extreme example, so it's really obvious to see what has changed. So I'm just going to pull one of those faces, and then all I have to do is return to my AFEM and tell it that I have some updates for it to integrate. And then just within a few seconds here, it's going to remesh that component and then remap it, remap that updated mesh. And then you can see we have that update propagated throughout our entire assembly FEM. So once again, just great feature about SimCenter is leveraging that geometry associativity to be able to do these types of updates really easy in tandem with those synchronous modeling tools within your idealized part. This just is something that's so useful for design iteration and being able to quickly play around with design changes in your model. And this is something I use all the time in my finite element model process, often for recommending maybe thickness changes to deal with negative margins or subtle design changes that can be implemented into the design. And yeah, just something I really appreciate how you can iterate on design changes like that so easily. So I just did one more iteration just to show you one more time how quick it is. Just another quick, kind of more reasonable update for those corner brackets. And now let's talk a little bit about what if you want to change your representation of components within the assembly FEM. So for example, maybe for one of these instances of these tubes, you actually instead want to use a super element representation. So you can do that easily. So this will just take a second to import. So essentially what I did is I solved a super element boundary condition model for this tube. And then I'm able to use the AFEM to connect to that relevant OP2 file. And then it'll actually use that super element representation for your tube, if that's what you want to do. And you can see it has all of my relevant boundary nodes for that super element model. So features like that, really useful. The fact that you can just do that within the assembly FEM rather than having to do it in the text editor or a more manual method like that. You could do things like replace an individual component. So if for whatever reason, maybe you don't want to have to modify your geometry or you just want to quickly iterate on design, you can instead replace your components, replace the FEM with an individual updated finite element model. You could do things like maybe you want to reposition one of these FEMs manually with a coordinate system within the AFEM. You can do things like that. Again, you're essentially breaking your mapping of your assembly FEM when you do things like this, but you do still have the option to do so and can potentially be useful for once again quick iterations on design or changes. So for example, I just repositioned this tube. You can do things like that. Um, so yeah, once again, Simcenter is just so great about giving you all these different options to accomplish your goals. So really just useful features and being aware of all of your different options within your assembly FEM is just something I wanted to really highlight today. Next, let's talk about dealing with our node and element ID conflicts within the assembly FEM. So we can leverage the assembly label manager for this. So for the assembly label manager, you can see currently a bunch of red X's here, which are indicating that we have some conflicts, which makes sense. We have multiple iterations of these FEMs here, and all of them have the same node and element ID range currently because they're all copies of that FEM. So what's great about the assembly label manager is it allows you to deal with these conflicts and automatically resolve them just within this one dialog box. So what you can do, and this is what we're going to do in this case, is tell it, hey, across nodes, elements, physical properties, groups, and so on, I want you to use the same offset. And you can also specify to the nearest kind of 1EX value that you want that offset to occur. So for example, I'm going to do to the nearest 1000, and then I'm going to click automatically resolve. And it's going to automatically set the relevant offset such that you no longer have those ID conflicts. And it's going to use that same offset again across my nodes, elements, coordinate system for each of the same iteration of those individual FEMs. So really useful feature again here, allows you to, instead of dealing with trying to manually renumber things, you can just automatically resolve it within this assembly label manager. And you do still have the option, if you wanted to manually define offsets. This is something really useful again as a time saver, and also this way you have a good understanding when you're doing post-processing steps, for example, and you're probing your peak stress node or things like that. You can have a good understanding of which exact iteration of the FEM and location that was coming from, which can potentially be useful. All right, so with that, our assembly FEM is essentially done. But what if we were to have multiple iterations of a subassembly? So for example, what if we have multiple iterations of the same assembly that we've been working on here? So in this case, we essentially have two of them stacked on top of each other. So once again, we can create a new assembly FEM. And now what I can do is I can map that AFEM that we just created to these existing sub-assemblies here. So instead of mapping new, I can do map as existing, and I can point it to those AFEMs, or that AFEM, excuse me, that we just created. So yeah, I just really wanted to showcase that you can, in fact, have kind of nested AFEMs within an AFEM. So once again, you can break out your sub-assemblies to their own AFEMs and then have individual component FEMs within those AFEMs, which is really nice as well. And then once again, we can use the assembly label manager within our assembly FEM here to deal with these conflicts automatically. So again, just huge time saver. Just click of a button here. My ID conflicts have been dealt with. All right, so now we do have a mesh we can move forward with and go ahead and define some relevant connections. So for today's example, I'm going to talk about defining bolted joint connections using the bolted joint connection tool that we can use within our assembly FEM. So I'm just going to go ahead and set up some useful groups. And what we're going to do is essentially just define some bolted joint connections between these sets of corner brackets right here. All right, so again, we're going to use that bolt connection tool, which is right here. And this is a really powerful tool that I really want to make sure everyone is aware of. If you've done bolt to joint modeling in the past, you probably know it often involves creating spider elements on your bolt head side as well as the threaded side. You're doing representing a bolt in a tapped hole. And then you will usually have some sort of joint element between connecting those spider elements. And that's often represented with a bar element or a spring. And that essentially represents your overall kind of stiffness of your total joint. But what's great about the bolt connection command is rather than having to do those operations separately, this is going to go ahead and create those spider elements as well as that joint element all within one command here, which is so useful and can really save a ton of time. So for example, let's go ahead and do our bolt and tapped hole. And for the head side, it's looking for cylindrical edges that it wants us to select. So instead of manually selecting 16 edges here or trying to draw a box to do that easily, what we're going to do is leverage our smart selector methods. And these are really powerful as well that I really want to make sure people are aware of. So these are essentially selection tools where, for example, I can tell it I want you to select circular edges. I can tell it which geometry I want it to select those relevant edges on. And then you can also give it a min and a max radius, and that'll be how it determines what it wants to select. So you can see it grabbed a bunch of edges, some additional ones that we don't even want, but then we can actually do easy things like just deselect some of these edges. So yeah, really helpful feature there, something I definitely recommend. Taking advantage of these smart selector options. Actually accidentally deselected some additional ones, so I'm just going to go ahead and run that through once again. There we go. All right, so we have our 16 edges that we are looking for, and then we can go ahead and deal with the tap surface side. So now the command is looking for cylindrical face selections, so we can essentially use our smart selector methods once again, and it's going to grab all of our cylindrical faces that we want. So you can see just with a couple clicks here, we're able to grab all of these faces rather than having to do more manual operations, which is so useful. Definitely recommend leveraging those smart selector options. So now we have our selections complete. Now you can define things like bolt length or effective threaded length. In this case, we're going to represent that joint element with the C-bar. So what the bolt length is going to do is essentially determine the length of that C-bar, and the effective threaded length is essentially going to determine where the position of our or like the amount of material that that threaded spider is grabbing. And then for our spider elements, we're going to go ahead and tell it to use RB2s. So then the command has been run. So what we can do now is zoom in, and you can see we do get our sets of spider elements on one end, our joint elements on the other end, and then our other set of spider elements. So yeah, a really powerful command there, that bolted connection tool. Definitely recommend taking advantage of if you're doing a lot of bolted joint connections. And what's another nice feature about it is, for example, you can actually go back after running the command and change the parameters and actually have it update. So you could like, yeah, change what your joint element that you want it to be, things like that. So yeah, really, really great command that I've been leveraging a lot whenever possible. And then as always, we can use our useful visualization tools within SimCenter. So for example, I can go ahead and define a diameter for that C-bar element. And then I can go ahead and turn on my display here, my solid display, so I can actually visually confirm that those C-bars seem to have the diameter I expected or I believe to have defined. So yeah, really, really nice feature there as well. So with that, we've essentially created the relevant connections within our assembly FEM. Now let's talk a little bit about creating some connections within our simulation file. So with the main types of connections that you create within your simulation file are within our simulation objects. So for example, if we expand these, you have a few different options here. Most relevant are glue or contact types of definitions. So for today, I was just going to briefly talk about setting up our glued connections and how you can leverage those for large assemblies like this. And what's so great is, once again, we can use that geometry associativity to create these types of connections. So for example, we can do our surface to surface gluing. And if you wanted to, you could do manual connection. You could manually define your source and your target. But we're going to leverage our automatic pairing capabilities here. So what I can do is similar to a lot of these commands is just select the relevant bodies and then specify an appropriate search tolerance that it's going to use to create all of these different types of glue connections. So you can see if we look here now, it's saying it's grabbed a bunch of face pairs based on that tolerance. And then you have the ability to define your Nastran glue parameters here for the individual glue connections. You can also define global glue parameters within your simulation definition. But yeah, as you can see here, within just a couple clicks, I've gotten 196 glue connections automatically defined for me, again, based on the search tolerance that I specified. So yeah, really useful feature again here to leverage that geometry associativity such that, yeah, you don't have to do a bunch of manual creation of these types of connections. If this is what you're trying to do in your model, you can really use your geometry and that automatic creation tool to save you a ton of time. All right, so with that, our model is essentially done. Let's talk a little bit about post-processing now. So we're going to jump into a version of the same model where I've solved two different solutions for us. That way we don't have to be solving a model live here. So solution one, that is just a lateral gravity load, and then we have a free mode solve. So starting with our free modes, we can go ahead and start looking at things like displacement to look at mode shapes. So you can also see we got 6 rigid body modes, which is great. It's always important Nastran check to do. So yeah, when we start looking at our flexible modes here as an example, tons of widgets here available within the post processor for common settings. So you can do things like turn on banded contours. Maybe you want to turn on element edges. You can do those very easily with a couple clicks. We're looking at mode shape right now. So one of the most relevant is looking at animations. So for example, do a modal animation. You can tell it number of frames. You want it to be full cycle, and you can animate that. And then what's really useful is being able to export that animation to a GIF file. And this is something I always do with deflection plots or animation, or excuse me, modal plots. I always export these animations and include them in my PowerPoint presentations or send to customers, things like that. And such a useful tool for being able to make sure people understand what's going on in your model, and that they actually understand the mode shapes or the deflections, because often you just give a static picture. It can sometimes kind of be unclear what the actual mode shape is. So yeah, really definitely recommend taking advantage of being able to create those animations wherever possible. Next, let's go ahead and look at that lateral G load model. So let's start with looking at some stress results. And then we're going to go ahead and open our main post processor setting toggle here. So we have tons of different options in here. For example, for shells, we can turn on where the shell stress is going to uh, be documented. So you can do top, bottom. In this case, we'll just do maximum. We can turn on things like nodal averaging. You have the ability to change your units, your stress units, or change the scale factor. You have the ability to turn on relevant deformations. So right now it's just going to default to essentially a percentage of the model for my deformation, which may be a little hard to interpret. So what I like to do a lot of the times is change it to be a function of my absolute deformation. So maybe I just want to look at 100 times absolute. You can do that easily. And then you can also do things like change your color bar such that maybe I want to say, okay, I'll stress above 20 MPa. In this case, it's going to have be shaded gray within my element contour. So I can let that go. And now if you zoom in, you can see all of those gray elements here. And this is something I'm always using when I create stress contours, is doing capping like this. It can be such a useful thing, particularly if you're showing negative margins. You can say, hey, all the stress in gray are stresses that result in negative margins when you include relevant safety factors. So really powerful feature there, and something I appreciate about the software is how easy it is to set up that color bar really quickly and kind of get all the settings you want there. All right, and then the last thing I wanted to talk about with our post processing here is snapshots and post templates. If you've done post-processing in Simcenter, you're probably aware that if you exit the post-processor and then have to, I don't know, for whatever reason, you have to resolve the model or just close your current working Simcenter instance here, you're going to lose all of your post-processing settings. They're just going to go back to the default. That's why it's so important to leverage your post-processing templates and or snapshots. So right now, right, we've changed a bunch of settings. We've played with the color bar, turned on nodal averaging, etc. So what the post template is going to do is that's going to save all of those post-processing settings. But what the snapshots are going to do, it's going to save all of our post-processing settings, and it's also going to save all of our current view settings. So I'm going to get a distinct view here, and I'm going to create a new snapshot. And not only that, it's also going to maintain whatever components you have, or FEM components you have turned off or on. So if we go over here, you can see within our post view here, we have our assembly structure maintained, which is also really useful. Again, with these AFEMs, we have all these FEMs mapping our exact AFEM structure. So what we can do is we can turn off individual FEMs easily. And then what we can do is create a second snapshot for this. And then let's go ahead and exit the post processor and immediately jump back in. So now let's first use our post template. If we use that, it's just going to, again, it's going to load all of those template post-processing template settings that we had just established, but it doesn't save any of our views. So once again, though, we can use our snapshots to get back to the exact same view and post-processing settings that we have established. And then we'll look at that second snapshot, which hid those components. So incredibly useful feature. This is something I am using every single time on post-processing. I use it a lot to define individual snapshots for individual components, such that you can get maybe that really nice looking stress picture for an individual component. And you can do that for all of your components within your assembly. And that's just going to save you so much more time when you have to run additional load cases or design iterations. You can potentially uh, already have all of those contour pictures ready to go. And then you can also do things like this where you can export all images. So all these snapshots, you can export all of them as images automatically. And you have options for the formatting of those image files. And then be able to immediately include those pictures in reports. So yeah, again, you can imagine just the power of being able to set up all these snapshots, export all those images, and then you have those all ready to go to throw into a Word document or a PowerPoint presentation, whatever it may be. All right, so with that, we've essentially have walked through our entire FEM process here. So yeah, to recap, what we've talked about is um, creating individual component FEMs for AFEMs and how those can be mapped to all of the instances of those components within your assembly FEM. We talked about some additional tips and tricks in regards to mid-surfacing and things like that, and leveraging your assembly load options within your AFEM to be able to have people working on their sub-FEMs or sub-AFEMs within their own folders. We talked about what happens when you modify a component and how that propagates throughout your entire AFEM and how easy that is with leveraging your geometry associativity. Leveraging powerful visualization tools within Simcenter, like your element edges and element colors, and how you can actually set those within the customer defaults. The assembly label manager, which is again so useful for being able to deal with node and element ID conflicts, things like that. And then creating connections within your assembly FEMs that mainly included the bolt connection tool, as well as the glue connection within your simulation file. And then finally, we talked about all those post-processing tips and tricks. Really just want to call out again, using those animations as well as those snapshots for really not only improving your efficiency, but creating those really powerful images to include in your reports. So with that, we'll go ahead and open it up to if there's any questions. You can go ahead and feel free to put them in a chat or unmute yourself. And yeah, thank you.